Hello everyone, and welcome to the second lecture of the second seminar, second lecture series of several intro to several complex variables. So Ravi will continue his discussion from the last time, and he'll be talking about Levi pseudoconvexity of the domain. So over to you, Ravi.
Yeah, thank you, Agniva. So, can you hear me right?
Yes.
Okay. So, let's recall what we did last time. So, last time we have defined the defining function and studied the analytic convexity of domains. Okay, so let us recall the theorem which we proved last time. So, let D be a bounded, compactly contained domain in Rn, and basically we have a strongly C2 strongly convex domain in Cn. Okay, in Rn, then there exists a global defining function say root tilde of D such that, so this is our defining function such that comp this real Hessian jk from 1 to n del square rho by del x j del xk at p wj wk is strictly positive for all w non-zero which is in Rn and for all p in boundary of omega. So we'll use this theorem to prove one important result. So let us state. So now what we will prove? So the proposition. So we'll prove that if the domain is a strongly convex domain, then it is a convex in a usual sense. That is, if x and y are in a domain, then tx plus 1 minus ty is also in a domain. So let me write the proposition first. So I am saying let omega subset of compactly contained in Rn be a C2 smooth strongly convex domain. Then for each z comma w in omega will imply tz plus 1 minus tw is also in omega for all t between 0 and 1. So we'll okay, so the more general result is true, but I will prove this simple result. This we will prove using the connectedness argument. So we'll define S, which is like uh, P comma Q in omega cross omega, such that Tp plus 1 minus Tq in omega for all t between 0 and 1. So note that omega is connected, so omega cross omega is also connected. So if we can show that this S is connected domain, then we can see that S is exactly omega cross omega, and we will have the geometrically convexity means this result, this star. Okay, so first, so we have to prove this is basically open and closed in omega cross omega. So first we have to show that the S is non-empty, and this is easy because if you take any p in omega, then you can see that p comma p is also in omega using the definition. And now to show that S is open, so for S is open, take any p So say this is omega. Take any p comma q in S, then by definition of S, this line joining from P to Q will belongs to domain omega. And since this line is compact in omega, so we can find a cylindrical neighborhood inside omega, something like this. So now we can say this is some u of p and say this is some u of q, and this cylindrical neighborhood will lie inside omega because of the compactness of this line. So now here we can easily see that this up cross uq is also in S, because if you take any point in UP and any point in this UQ, if you join the line, it will be inside this cylinder, and cylinder is contained in omega. So we'll get UP cross UQ is in S, which will imply S is open. So now the remaining part is to show that S is closed. So if we can show that S is closed, then we are done, right? So now the claim is S is closed, and note that this is not closed in Rn. This is we have to prove just closing omega cross omega. So we'll prove using the sequential criteria. So that means let so if Pn comma Qn be any sequence which is in S, and Pn comma Qn goes to some P comma Q. So we want to prove P comma Q is in S. So if we can show that P comma Q is in S, then we are done. Then we can prove, then this S is closed. Okay. So since Pn comma Qn is in S, so by definition Tpn plus 1 minus Tqn is in omega cross omega for all t between 0 and 1, and for all n in natural number. So since Pn comma Qn goes to P comma Q, this will imply this is Tp plus 1 minus Tq. Oops, sorry, this is omega. This is in omega bar actually. So here we have a two case. So case one, so if Tp plus 1 minus Tq is in omega for all t between 0 and 1, then we are done. Then we will have P comma Q in S. So now the case 2. So if there exists T naught positive such that T naught P plus 1 minus T naught Q is in boundary of omega. So here we will have to use the previous theorem which I stated. Okay. So how can we use it? And here note that P is not equal to Q, because if P is equal to Q, then it is obvious that P comma Q is in S. So we'll define G of T, which is rho tilde is, we have taken a defining function which satisfies the property or estimates of theorem 1. So rho Tp plus 1 minus Tq. So here note that this G is a function from 0 1 to R minus union 0, because uh, this quantity is always in omega closure. So our g is always less than or equal to 0. And g is equal to 0 at the point t naught. So that means g has a maximum at t naught, which will imply g double prime at t naught is negative or less than or equal to 0, because you can see that by our assumption on case 2, t naught is a local maximum. So if you write g double prime in the Hessian form of rho tilde, you will get this is this is by using chain rule. J k 1 to n del square rho tilde del xj del xk at the point t naught p plus 1 minus t naught q p minus q j and p minus q k, which is negative. And this will contradict our assumption on strongly pseudo-convex domain, because for strongly convex domain, because for strongly convex domain this condition is strictly positive. So here we'll get the contradiction. So this is the contradiction. Okay, let me write. So this will contradict the assumption of a strongly convex domain. D. So this will imply, yeah, so what will imply? This will imply that the case 1 is the only possibility. That means Tp plus 1 minus Tq is always in S for all t between 0 and 1. So this will imply, oops, it is always in omega. So this will imply S is closed. And we have proved S is closed, open and non-empty, which will imply S is exactly omega cross omega. And hence we have proved the theorem. I hope it is fine. Okay. So now we have proved that if our domain is, so what we prove here? So we prove if we have omega which is strongly convex. Then we prove that uh, and and our domain, yeah, domain, we are taking domain, so which is connected. So that means we prove if you take any p and q, then the line joining p and q is also in omega. So now we'll state one more result, which is saying that, so take any domain omega and yeah. So we have omega, say omega tilde, and say this is analytic convex. Analytic convex means its Hessian is positive on the tangent line, which I have defined in last lecture. Yeah, analytic convex, and say omega tilde is a C2 domain. Then also if you take any point P and Q, and if you take a line joining them, then this line will also contain in omega. And the converse is also true. So let me write the statement of the theorem. So the theorem basically saying that let omega be a compactly contained subset of Rn be a domain, be a C2 domain. Then I am saying that omega is analytic convex if and only if for each z comma w in the domain will imply tz plus 1 minus tw in omega. So this result I will not prove, but I can refer you where you can find the proof. So you can look at the Kranz book. Kranz book. This is, I think, SCB book. Yeah. So the idea is to, so we'll give, I can give the idea. So here, if you have to prove the forward, then if you take any omega which is analytic convex, then you can exhaust this omega by strongly convex domains. And for strongly convex domain, we have proved in the last proposition that it is convex. So using the previous result, you can prove that this analytic convex domain will be strong, geometrically convex. And for the converse, you have to use the uh, defining function and the Taylor series of defining function to prove the converse. Yeah, so you can, so I have given just the idea, so you can look at this converse.
Analytic,
Uh-huh.
analytic convex means this Hessian will be
Okay,
positive on this tangent space, right?
correct. Yeah, yeah,
Okay.
that's what I've defined last time. Yeah, means the Hessian is positive or greater than or equal to zero on the real tangent line.
Real tangent, yes. Okay.
Yeah, yeah. If it is pseudo convex, then it's complex tangent line that I will define now. So now
Mm.
we'll move to. So now we will move to uh, convexity in the complex tangential direction. Okay. So let, so we'll define, so let omega compactly contained in Cn. So now we are in Cn. We are domain and P is in the boundary of omega. So so for that we have to define convexity in the complex tangential direction. So first we will have to make sense of what is complex tangential direction. So first let us recall what is the real tangent space. So let's say omega has so this is omega, and say this has a defining function rho. Then the TP boundary omega is those W in Cn such that j from 1 to n or 1 to 2n del rho by del xj at p. Okay. Psi j. I will explain what is I and eta. J from 1 to n and j from 1 to n del rho by del yj at p eta j, where w is like z1 plus iota eta 1 comma dot xi n plus iota eta n. So this is the tangent space. Okay, let me write. So now we have to. So what is the goal? So goal is to find a sub. Say okay. Let say s. Okay, yeah. Okay, I have used s already. So let's say w. So we have to find w, which is subset of TP boundary omega, and also this w should be complex linear subspace, because we want to see the complex tangential direction. So this should be complex linear subspace or complex, yeah, complex vector space. Okay, so how do we find or how do we define this type of W? So let us rewrite our, let us identify W in Cn to R2n. So, okay, sorry. So here, since W in Cn, so you can write W as W1 to Wn, and which is also you can write as xi1 plus iota eta 1 dot xi n plus iota eta n. And this you can identify by R2n using like this xi1 comma eta 1 dot xi n comma eta n. Similarly, you can also identify z in Cn as z equal to z1. So I'm just writing the notation for w and z in the Cn and R2n. So this is x1 plus iota y1 dot xn plus iota yn. So this is equivalent in R2n. Oops, sorry. Yeah. So this is equivalent in R2n like this x1 y1 dot xn yn. Yeah. So since if w is in TP of boundary omega, then we can write by definition this is j from 1 to n del rho by del xj. Yeah, okay, sorry for the this noise. It will stop in a minute. Del rho by del xj at p xi j plus j from 1 to n del rho by del yj eta j at p equal to 0. So this is just I am using the definition w is in TP boundary omega. So now our goal is to write this expression 1 in the complex form. That is, so for that we'll define the del by del zj and del by del zj bar. And this I think Agniva is defined in his lecture series. So let us recall from Agniva's lecture series that del by del zj is nothing but 1 by 2 del by del xj minus iota del by del yj and del by del zj bar is 1 by 2 del. So okay, here I am doing little bit of computation, yeah, but it will be worth to do it. Xj plus iota del by del yj. So from here we can see that del by del xj is nothing but del zj plus del zj bar, and del by del yj is 1 upon I del zj del by del zj bar minus del by del zj. Please also verify if this is true. Yes, yeah. And we can also have xij is wj plus wj bar by 2 and eta j is wj minus wj bar by 2i. So now we'll put the this del by del xj del by del yj xi zeta j eta j in the equation 1. So if we put the all the value of this zeta j eta j and del by del xj del by del yj, we'll get something like, okay, let me write directly. So if you put all this value, you will get real part of j from 1 to n del rho by del zj at p, and then this is wj equal to 0. So this is from 1. Yeah, so if you put all this value and if you do little bit of computation, you will get this set equation too. But we want to find the complex subspace. That means if W is in the, so we want to find, so we have W which is a subset of like TP of boundary omega. So we want this should be complex subspace or complex vector space. That means if, so let, oh man, sorry. Yeah, so that means if, sorry for that. Yeah, so that means if W is in capital W, then IW should also be in the capital W. So here we have seen that if W is in TP of boundary omega, then this is actually from equation 2. This is real part of J from 1 to n del rho by del zj at p wj equal to 0. But we also want iota w is also in capital W. So if you put iota w, then you will get imaginary part of j from. So if iota w is in also in say t tangent space tp of boundary omega, then from here you will get imaginary part of j from 1 to n del rho by del zj at p wj equal to 0. So motivating by these two equation and we want a complex space which contain in the real tangent space, we can define C of TP boundary omega, which is, so now basically, so this is complex tangent space. So we'll define this like those W in Cn such that J from 1 to n del rho by del Zj at P of Wj equal to 0. So motivated by above fact, we can define this complex tangent space. So now we'll write some remark of this complex tangent space. So remark 1. This CTP of boundary omega. So okay, so the first remark should be the well-definedness. So this complex tangent space we defined on some domain omega. So here we have omega, which is subset of Cn, and this is the point P. So here you can see that this complex tangent space we define using the defining function. So you can check that this is well defined. Means if you take any another defining function, then also you will get the same complex tangent space. So you have to use this fact. If rho1 and rho2 are two defining function, then you can write rho1 as h times rho2, and then you can check the well definedness. And the second remark is, if you have a let omega is a subset of C, then you can see easily or you can verify by yourself that the complex tangent space, so P is a point of boundary omega, is just 0 point. Means if you are in omega is subset of C, then this complex tangent space is just a trivial space. Okay. And the third one, this is what, this is how we define. So the third one is saying that this CTP of boundary omega is the largest complex subspace in TP boundary omega. Okay, let's that means what I am saying that is if you take any that is if you take S uh, uh, okay, let me rephrase the way I can write. Yeah. So that is what I'm saying that if S is a real subspace in TP of boundary omega, which is that is closed under I, then S is a subset of this complex tangent space. Okay, so the quick proof is something like if you take if so yeah, so we have to prove if S is of this kind exists, then S should be subset of CTP boundary omega. So if W is in S, then we know that, and S is a subset of TP boundary omega. Then we know that from previous calculation that real part of J from 1 to n del rho by del zj at P Wj equal to 0. And since S, I have assumed S is closed under I, that means iota W is also in S, which will imply imaginary part of J from 1 to n del rho by del zj at P Wj equal to 0. So if you combine this 3 and 4, you will get W is in the complex tangent space. So from here, we'll get that this complex tangent space is the largest complex subspace which contained in the real tangent space. Okay, so these are the three remarks on the complex tangent space. Okay, I hope it's the picture of this complex tangent space or the motivation will clear is clear by this remark. Okay, so now we'll move to define. So now we have a complex tangent space. Now, so now we'll define the convexity in the complex direction. So for that, again we have to move from the convexity in Rn to convexity in Cn. So how do we define the convexity in Rn? So let us recall. So let P, which is a point of boundary omega, is a be a point of be a point of pseudo convex point of convexity. So now we'll write, and we know omega is a subset of Cn. So now we'll write this convexity in the using the defining function. Okay, so that means we have this thing. So here W is in the TP of boundary omega. So this W we can view as xi1 eta 1 dot xi n eta n. Okay, and we can view z as x1 y1 dot xn yn. So if we write the real Hessian of the defining function, it will be look like jk 1 to n del square rho by del xj del xk at p xi j. Mhm. Is there echo? Okay, can you hear me? Am I audible?
I think some echo is there, Ravi.
Okay. Okay. Okay, so I'm joining again. I have logged out.
Okay.
Yeah, in meantime, if you have some question, you may ask. Yeah, so can you see my screen? Am I audible?
Yeah,
No, breaking voice is breaking. But there is
Yeah, Ravi, there is a echo. Ravi, you are muted.
Yes, let me give me 1 minute. Just.
Yeah, sure.
Now, am I
Yeah, now
audible?
it's fine. Yes,
Okay.
it's fine. But your screen is not visible yet.
Yeah, I'm sharing. Yeah. So where are we? Yeah. So let's see. Yeah. So what I am doing is, yeah. So we are moving from convexity to analytic analytic convexity to complex or say pseudo convexity. So what I have, let me write again. So let omega is a domain in Cn, and say P is a point of boundary omega. Okay, and yeah, so take let and say yeah, this is a point of pseudoconvexity. So sorry, this is a point of convexity. So let W is in the TP boundary omega. So we can identify this W by zeta 1, eta 1, dot, zeta n, and also we can identify uh, Z as x1, y1, dot, xn, yn. So, so if P is a point of convexity, so we can write the real Hessian in this form. So jk1 to n del square root del xj del xk at p zeta j zeta k plus 2 times jk1 to n del square root del xj del yk at p zeta j eta k plus jk1 to n del square root del yj del yk at p eta j eta k, which is positive. So so say this, the expression on the left, so this expression is say 4. So we will write, so as we write this real tangent space in the complex notation, so same we'll do here. That means if we write this, if we change this all this in a complex notation, so we'll get, so so if equation 4 will change in the complex, that is if we can replace zeta j by w plus wj plus wj bar by 2 and eta j as wj minus wj bar by 2I. And similarly for del, if we replace del by del xj in the form of del by del zj and del by del zj bar, as we did in the real tangent space, we'll get something like this. So I will write directly. I will not do the calculation, but you know the idea, so you can do the calculation if you like. So we'll get 2 times of real part jk1 to n del square row del zj del zk at p wj wk, yeah, plus 2 times jk1 to n del square row del zj del zk bar at p wj wk bar, which is positive. So, so the convexity meaning, if you write in the complex notation, will give this expression. Okay, so here uh, we will show that this expression, so basically this expression, the part inside the real with the complex number inside this real part, this is not biholomorphic invariant. But if you look at this part, so this is biholomorphic invariant. So yeah, so that means we want some notion which is biholomorphic invariant. So we'll consider this part of the Hessian. this we call the complex Hessian. So this is basically the Levi form. This is first introduced by Levi in 1910. That's why it's called the Levi form. And this form is nice because it is biholomorphic invariant. And that's what we want. We want some notion of convexity or pseudo-convexity, which is biholomorphic invariant. So this expression will do the job. Okay, so I will just give the sketch why this is biholomorphic. This box is biholomorphic invariant and why this is not biholomorphic invariant. Okay, so yeah, so take any omega here and take the neighborhood u, which is a neighborhood of omega closer. And we define the biholomorphism phi. So phi is a biholomorphism on u. So from that we'll get here phi of omega. And if there is a point P, then it will be mapped to some point here, say P prime. And assume if it has a defining function rho, then you can check that it has a defining function rho compose phi inverse. Yeah, so it is easy to check. Okay, so yeah, so we'll look at it. Yeah, so now we have to show that, uh, so we have two expressions. So say this is 1 and say this is 2. So we'll see after this biholomorphism. So say it has a coordinate z1 to zn and it has a coordinate z1 prime to zn prime. So we'll see that under this biholomorphism phi, this expression 1 is not invariant under biholomorphism, but this second expression is biholomorphic invariant. And note that here, if we restrict our W in the complex tangent space, because we want to do analysis on complex tangent space, it may not preserve if W is in just the tangent space, but not in complex tangent space. Okay, so let W, if W is in say complex tangent space of boundary omega, then W prime, which is the Jacobian of phi at PW, is also is in complex tangent of this P prime of boundary of say this phi omega is omega prime. So then this is the omega prime. Okay. Yeah. Okay. This you can verify using the definition of the complex tangent space. Okay. So now if you, so here you know all the thing. Rho prime means you know the relation between rho prime and rho. So I will not do the calculation. So what I'm saying that if you calculate jk 1 to n del square rho del zc del zk bar at p wj wk, this is exactly the same as jk 1 to n. The so this Levi form is in on omega, and we'll define this is in on omega prime. So here del square rho prime del wj wk bar at p prime wj prime wk prime, where wj prime and wk prime are the component of this w prime. So here you can see that this Levi form exactly equal if you are strict on this complex tangential space. But if you look at the this first expression, that is, sorry. So if you look at the first expression, that is, if you first expression is something like jk 1 to n del square rho del zj del zk wj wk. If you write this in the form of all the prime, means rho prime and W prime, then you will get something like JK12 and del square rho prime del ZJ prime. Okay, so here this coordinate is prime, so it's not W. This is del ZJ prime del ZK bar prime. Yeah, so similarly here you will get ZK prime at P prime, WL prime, WM prime,
Hello?
plus you will get some
Uh,
more term here. Yeah.
Hello. Since I mean the way you define this row prime
Mhm.
in the above picture, row prime is basically
Okay.
row composed
Yeah.
five moves, right? So, but to
Yeah.
define the
Five
boundary
modes.
defining function, we need this
Mhm.
smoothness on some. I mean, this row prime should be smooth on the some local bounded
Yeah.
of omega.
Yeah. Okay. Yeah. Good question. That's why I have taken. Yeah. Yeah. Just hold on. So that's why I have taken phi is biholomorphic on U. So that means phi is uh, how to say.
Okay.
So phi is biholomorphic on the bigger, means phi is smooth on a bigger neighborhood, just not in omega. So biholomorphic, what I mean that it is whole biholomorphic on a some neighborhood of omega closure, because
Yeah.
otherwise, yeah, as you mentioned that
Yes,
it may
we know.
not well defined.
Yeah, even it
Mhm.
is not homeomorphic at least. We can't extend any biholomorphic more than
Correct.
this.
Yeah, true. So we
Yeah.
need something like phi, which is biholomorphic uh, up to the omega closure or the neighborhood on the omega closure. Yeah, but later we can see that okay, there is some notion like if you have a finite type P, or if you have a finite type M, and if it is a biholomorphic in omega, then the finite type will map to finite type. But that is very deep analysis. So I am just restricting ourselves on this phi is biholomorphic on a neighborhood of omega closure to make life easier. Yeah, but it is good point. It means if phi just biholomorphic on omega, then we can't do this type of analysis here. Yeah. Okay. So yeah, if you compute this second term, then you will get some extra term here. So that means this term is not good in our case. And so that's why Levi consider this expression, which is called the Levi form. So now we are in position to define the pseudo-convex domain. So let's just quickly define. So definition, let omega subset of Cn be a, and I am taking C2 domain because otherwise this double derivative may not make sense if we are uh, if our regularity is less than C2. We are C2 smooth domain, and let P is in the boundary of omega to the point above the boundary omega. So the boundary omega is pseudo convex. So we say boundary omega is pseudo convex at P if this Levi form JK1 to n del square rho del zj del zk bar at P wj wk bar is positive for all w in this complex tangent space, which I have defined earlier. Yeah, so this is the definition of pseudo convexity at point P. Okay, similarly, as we define for convexity, we can have a strongly convexity. Similarly, here we say boundary omega is strongly pseudo convex at P if, so say this is uh, double star. If the Levy form, and we also call this is Levy form. If the Levy form is strictly positive for all W non-zero, which is in complex tangent space. Similarly, so yeah, this is say okay. So similarly, we say omega is pseudo-convex or in a bracket we can say strongly pseudo-convex. If for all P on a boundary omega is a point of strongly or point of pseudo-convexity. So basically what I've said that we see omega is pseudo-convex. If you take any point in boundary omega, it is pseudo-convex. Similarly, if we say our domain is strongly pseudo-convex, if you take any point P, then it is strongly pseudo-convex. Okay, so now we'll look at, so here we can also ask the same question, why this definition is well defined. So again, you can use, because this definition is depend on this defining function rule, but you can check that if you have a two defining function, then this double star is same for uh, both defining function rho1 and rho2. So you can again use this trick, using this trick that rho1 is equal to s times rho2. Okay, so this definition is well defined. And remark. So the first one, this is well defined. And the second one, uh, so if you take any domain in C, then can anybody guess is this domain is pseudo-convex or not? Yeah, so like we have seen that for the domain in C, the complex tangent space is just the trivial. So that means there is a no complex tangential direction in a domain C. That will imply that this D is always pseudo-convex. Because there is a no complex tangential direction in domain in C. That is the one of the big reason between the domain in C and domain in Cn. Yeah.
So
Okay.
Ravi, just a small thing. Like
Mhm.
here you mean by D as a bounded C to smooth, na?
Yeah, yeah. Okay.
Yeah.
Yeah. Our whenever I
Yeah,
say our
understood,
domain, so
understood.
it is bounded C2. Yeah. Okay. So that means these pseudo-convex. Okay. So the third is there. Okay. So okay. So say lemma. This is just a quick lemma. I will prove in a 2 minute. So let d be a, okay. Just stick on omega. Let omega be a subset of Cn be a C2 smooth domain and assume omega is convex. Then omega is Levi pseudoconvex. So we can prove this lemma because we have already uh, computed, or we have already uh, we have calculated some convexity condition with respect to the complex direction. Okay, what I mean, so we have to show that omega is pseudo-convex. So let's take any point P on a boundary omega. Okay, then so we have to show it pseudo-convex. That means if we have a W in the complex tangent space, we have to show that the Levi form is positive. Okay, but from our definition, this complex tangent space is contained in a real tangent space, and we know this P is a point of convexity because of this our assumption. So since P is a point of convexity, so that means it will satisfy the convexity property, which is basically saying that if we write that real Hessian in a complex form, we'll get something like this: 2 times real part of jk 1 to n del square rho del zg del zk bar, no, del zg del zk at p wc wk plus 2 times jk 1 to n del square rho del zg del zk bar at p wc wk bar, which is positive. So in a convexity, this expression is coming by this calculation. Let me show you. Where is it? Yeah, here. So actually, this is the condition of convexity, but we can see, we have seen that if you put all the if you rearrange in the complex form, you will get this real Hessian. You can write in this form. That's what I have written here, this thing. And also note that if W is in the complex tangent space, then iota W is in also in the complex tangent space. So if iota W is in the complex tangent space, that means this expression says 6. Here you can replace W by iota W. Then also this inequality is true because iota W is in also in TP of boundary omega. So this will imply, so if you put iota W in the expression 6, you will get, like here I square is -1, so you will get minus of 2 times real part of jk 1 to n del square rho del zj del zk at p wj wk plus, yeah. And also if you replace here w with iota w, you will get just 1. That means there is a no sign change here. That is, we can write this. This is exactly the same thing. If we replace w to iota w, wj wk bar greater than or equal to 0. Say this is 7. So if you add 6 plus 7, you can see that this and this will cancel. So basically you will get from 6 plus 7 this Levi form. So this is 2 times. So we will get 4 times. So 4 we can. So basically we'll get jk1 to n del square rho del zk del zk bar at p wz wk bar is positive for all w. So where we took the w, so we took w is in the complex tangent space. So this is for all w in complex tangent space. So this will imply sorry, yeah, so this will imply um, Okay, so let me write again here. So basically what we get, I don't know where that thing went. Yeah, so basically we get jk. So if omega is convex, we get del square rho del zj del zk bar at p wj wk bar is positive for all w in complex tangent space. So that means, so this will imply this point P is a pseudo-convex point. So here we can say that if domain omega is convex, okay, yeah. So this basically saying that if omega is convex, then omega is pseudo-convex. Or it's saying basically more than that. If the point P of the boundary is convex, then the point P of the boundary is a point of pseudo-convexity. And what about the converse? So can anybody guess, is the converse true or not? That is, if omega is pseudo-convex, is it necessary it is convex?
No,
So
not yet. In C, if you choose non-convex set.
yeah, right. Yeah. So that's why, yeah, I have given one remark. So if you take any domain in C which is not convex, but we can see by definition it is pseudo-convex. So this is in C. Yeah. So okay. There are some also example of pseudo-convexity and strongly pseudo-convexity, and there are some nice property of strongly pseudo-convexity, which I will give in our next lecture. Yeah. So today I have introduced pseudo-convexity using the real analytic convexity, and we defined this complex tangent space. I have discussed some nice remark. Yeah, thank you.
Yeah, any questions? All right, if there is no questions, so thanks Ravi for the talk. Yeah, see you then next lecture.
Yeah, thank you.
Thanks. Thank you.